Welcome back, Physical Science 20. So this is the FC1.3 double replacement reactions, the first part. So we just did single replacement. Let's look at what double replacement looks like. So we'll observe and analyze double replacement reactions, represent them using manipulative skeletal equations, balanced chemical equations, and IUPAC naming. Predict products of double replacement reactions, including acid-base, neutralization reactions, and also precipitation ones using solubility rules, which we'll see. And describe how the outcomes of various double replacement reactions may benefit or harm living organisms and affect the environment. So double replacement reactions or double displacement. So if we look at industrial processes produce unwanted products, dissolve toxic metal ions, copper, mercury, and cadmium are common leftovers in wastewaters. These toxins must be removed before the water can be released into the environment. In the single displacement section, you learned that some metal ions can be recovered as solids by allowing a solution of ions to react with a more active metal, so it replaces it, and that dissolved metal comes out as a solid. Another way to remove unwanted ions is to precipitate them. Now, what a precipitate is a solid that forms as a result of the reaction of two solutions. Chemists have found that adding sodium hydroxide to a mixture of waste metal ions causes most toxic ions to form metal hydroxide precipitates, as seen in the figure above. And we'll take a look at what's so special about the hydroxide portion of that. The mixture is then filtered to remove the precipitates. Copper ions can be removed from solutions containing waste copper 2 sulfate ion by adding sodium hydroxide. So if you take a look at what's going on here, so copper sulfate, aqueous, sodium hydroxide, aqueous, okay? So we have our metal and we have our non-metal group. Metal, non-metal group. So it's a case of, again, will there be a replacement? But this time we don't have a single element replacing one that's in a compound. We have element in a compound replacing element in a compound. If you take a look here, copper and hydroxide, sodium and sulfate. So we have them exchanging places. And one of them could be a solid or that precipitate that we're talking about. So a solid that comes out and just settles on the bottom of the beaker, and we have this liquid on top. A closer look at the equation shows that sodium and copper ions in the reactants have traded places or displaced each other. Chemical reaction in which two elements from different compounds displaced each other is called double displacement or double replacement. So the general equation for a double displacement reaction is simply this. Like we've seen before, very similar format here. So again, we're seeing do the metal ions exchange places. So we're seeing if that happens. And if they do, we now have A with D and we have C with B. Bear in mind the metal is always first. So A is always first and C will be first with that puzzle. So you can imagine if I go back to my weird analogy, yes, guy, girl, and guy, girl. So it could be like a square dance. Did they change partners? Let's see here. So A will be with the one written in pen. And this guy and this girl change partners in the square dance, indeed. So types of double displacement reactions. We'll look at two different types here. So double displacement reactions vary, resulting in different products. Some produce precipitates, and we'll see how that happens. And others result in solutions that are more neutral than the reactant solutions. We can classify double displacement reactions according to the type of product they generate. So we'll look at precipitate ones first. So when two solutions react, positive ions, or the cations, in one solution attract and bond to the negative ions of the other one. Just like here, this positive combines with this negative potentially. If the new compound precipitates, it must be only slightly soluble, which means it doesn't dissolve really well. Before we can predict which compound precipitates, we need to understand some key ideas related to solubility first of all. So a solution is a homogeneous mixture. That means it looks like one thing, one solution, of a solute and a solvent. So we can imagine a solute plus solvent makes a solution. For example, an aqueous salt solution is a mixture of a salt dissolved in water. So water is the solvent in that case. Solubility is defined as the amount of solute that will dissolve in a quantity of solvent. So if I have a certain amount of water, how much of whatever substance can I dissolve in it? And of course, solubility of the solute depends upon factors such as type of bonding within the solute, the states of both substances, and the temperature. And as you saw back in Science 10, if you increase temperature, you can increase how much you dissolve. All substances dissolve in water to some degree. Some chemists describe a substance as very soluble or highly soluble if we can dissolve a lot of it. A substance that does not dissolve very well is referred to as slightly soluble. In the equation of a precipitation reaction, state symbols indicate which of the products forms a precipitate. And that symbol S, which we looked at earlier, means solid. Can also mean that precipitate, that solid that comes out of the solution. The symbol AQ indicates something that's still dissolved in water. So predicting precipitate, selecting the correct reactant to precipitate metal ions from solution requires background knowledge of which metal compounds are soluble and which ones are not. This information is summarized in the solubility table, as you can see below. This table is a summary of different combinations of ions. It tells us the combination of ions that produce compounds that are either very soluble, so they dissolve really well, or they don't dissolve very well. So for example, the table states that all hydroxides of the group 1 elements are very soluble. So if you look down here, if I have hydroxide, and if I go to this side, so everything is a slightly soluble, which means it forms a precipitate except group 1 ions and also calcium, barium, and strontium. Therefore, we predict sodium hydroxide dissolves readily in water. Conversely, most other cations form hydroxide compounds that are only slightly soluble. Therefore, mixing a solution of copper with sodium hydroxide would make a precipitate. So hydroxide combined with copper will go to this side. But we'll take a look at this table right now. We'll try to make head or tail of what in fact is going on here. So first of all, you look up the negative ion first in whatever substance you have. So that's kind of what we look at. And this side here is kind of the default answer of what it will be. So if we have an ion with most ions, with most positive ions, this is the side we're going to look at. And then over here we have small exceptions to the rule. So over here, if I look here, if I have nitrate, or if I have chloride or other halides. Now halides, I just simply mean halogens. You may want to write halogens. So chloride or any of these ones in the halogen group. Okay, this rule is followed. Sulfates, acetates, sodium, potassium, and ammonium. So if I look here, most of the time when I have any of these negative ions with any positive, I'm going to go to this side right here by default, which means very soluble, no precipitate. Or I like to call precipitate PPT, just for shorthand. P, P, and T make up precipitate. So these exist in aqueous form. Okay? Exceptions to the rule, if I had chloride with copper 1, then I would go to this side, and this side means, let's just make this funky bracket like this, down to where things get weird with part 2 here. So we can put, we will put slightly, so it slightly dissolves, slightly soluble, forms PPT, and slightly soluble means there will be a solid. Let's just get this paper out so you can copy that out. So it makes a precipitate, a solid, due to being only slightly, that should be an S, slightly soluble. So that occurs right before we get down to this part. Okay. Now, if I look at the bottom ones, they're vice versa. As mentioned, hydroxides by default with most things are slightly soluble. Forms PPT. So most things with hydroxide don't dissolve very well. So they make a precipitate. And again, if I go look at the exceptions though, if I had hydroxide with calcium, it won't form a precipitate, it dissolves. It is very soluble, so it'll be considered AQ, and I can simply write no precipitate. No precipitate. So it exists as dissolved ions in solution. Okay, so that's how that table is set up. You have the left-hand side and you have the right-hand side. We have ions that are dissolved in most everything. Then you have ions here that with most metal ions form a precipitate. They don't dissolve very well. So the reactants don't have to be in solution when they are combined. As long as they're both very soluble and both add to water, they will dissolve. Okay, what we'll do is we'll stop the video there, and then we'll come back and look at an example and look at a couple more examples. All right, we'll see you soon.